Hello, everyone, welcome back to the channel Future Force. Please subscribe and like my videos. Today, we are diving into a full, detailed analysis of a dramatic event that captured global attention. The coordinated drone strike involving 93 Ukrainian drones that targeted Moscow. This is more than an incident report, it's a case study in how modern unmanned systems are changing the rules of engagement, testing defenses, and forcing military planners to reassess what distance and security mean in the age of swarm tactics. Over the next several thousand words, I'll walk you through the exterior design of the drones, the deep interior systems that make them lethal and resilient, their performance characteristics in a complex mission, the safety and fail-safe features that are built into these platforms, the unique selling points that make them tactically valuable, the economics and pricing realities of drone warfare, and a concluding synthesis of what this strike means for the future of conflict. This is not a short primer, it's an in-depth technical and strategic breakdown aimed at anyone who wants to understand how small, relatively inexpensive machines were used to project force into the heart of a heavily defended capital. When we first look at the exterior of these drones, the defining characteristics are simplicity, modularity, and stealth-oriented practicality. A frontline combat drone is rarely built to be beautiful, it is built to be effective. That means aerodynamic shapes optimized for low radar cross-section, lightweight composite materials that balance strength and cost, and finishes that reduce visual and infrared signatures. Many of the platforms used in long-range strike roles are elongated, with slender fuselages and relatively small wingspans that allow efficient cruise but make them harder to detect against a low-lying horizon. The surface treatments are matte or low gloss to avoid glint in sunlight, while the color palette tends toward grays and muted tones for night and twilight operations. Beyond stealth, the exterior often features quick-access panels and modular hardpoints, so payloads can be swapped in the field. A reconnaissance payload one day, an explosive module the next. Propulsion units, whether small piston engines, electric motors with high-density batteries, or compact jet turbines, are integrated cleanly into the airframe to reduce drag and thermal signature. Externally, you'll also find mounting points for small satellite or data link antennas, optical sensors in protective housings, and absorbent materials around vulnerable seams to reduce detection by radar and acoustic sensors. All this results in an exterior that is less about aesthetics and more about survivability, cost efficiency, and quick turnaround for repeated sorties. The interior of these drones is where their real sophistication lies, and this is where I want to spend a lot of time because the interior architecture determines capability. Inside, space is at a premium and every cubic centimeter is optimized for mission, critical systems, flight computers, navigation stacks, power distribution, propulsion interfaces, communications modules, sensor suites, and payload mechanisms. The flight control unit is typically based on a robust avionics stack with redundant processors and fault-tolerant software. Many modern tactical drones use a layered autonomy approach. A low-level flight controller handles stabilization and control surfaces, while a higher-level mission computer executes navigation plans, target recognition algorithms, and contingency behaviors. These higher-level functions increasingly integrate machine learning models for object classification and optical flow navigation, allowing drones to navigate without GPS when necessary or to cross-check GPS coordinates with inertial navigation and visual landmarks. The navigation subsystem itself is commonly a hybrid, GPS for long-range routing inertial measurement units used for high rate attitude and acceleration data, and optical or LiDAR-based systems for terminal guidance and obstacle avoidance. This hybridization provides resilience against jamming and spoofing if GPS is lost. The drone does not simply go blind. Instead, it can switch to inertial navigation and visual odometry to maintain course, or to execute pre-programmed behaviors like loitering, return to base, or self-neutralization. Power management inside these drones is complex and mission-specific. For electric or hybrid electric models, high-density lithium-ion or next-gen battery packs are arranged in modular trays with thermal management channels to prevent overheating. For internal combustion variants, compact fuel tanks and efficient engines are tuned to provide a long endurance profile while keeping acoustic and thermal footprints low. Power distribution systems include prioritized rails. Flight-critical electronics have hardened, redundant power sources with immediate failover, while non-essential payloads are on a separate distribution that can be shed in emergencies to conserve energy for flight. Cooling is not ignored. Sensitive avionics are protected from heat and electromagnetic interference through shielding and heat sink design, while exhaust paths are routed to minimize infrared signature. Structural design inside also anticipates battlefield conditions. Components are shock mounted, connectors are sealed against moisture and dust, and wiring harnesses are routed to limit vulnerability to shrapnel or small arms fire. Payload bays include stabilized mounts and vibration isolation, so targeting optics and explosive charges remain stable through maneuvers. Communications and electronic warfare EW resilience are also central to interior design. Drones intended for high-threat environments often carry multiple data link radios operating on different bands with frequency hopping capabilities and strong encryption to resist interception or takeover. Additionally, there are often fallback behaviors coded into the mission profile. If the primary data link is lost, the drone may switch to an autonomous program to continue to the target using onboard sensors. If navigation is severely degraded, it may hold pattern until commanded otherwise or execute a programmed return to base sequence. Some advanced platforms incorporate passive RF sensing so they can detect jamming or hostile emissions and alter course to exploit gaps in the electromagnetic environment. In the case of a coordinated mass attack, interior systems will often have synchronized timing mechanisms allowing swarms to converge on a target using decentralized protocols, reducing reliance on a single command source that could be jammed. The payload interface is another interior focal point. Explosive or kinetic payloads are mounted on control release mechanisms with safeties to prevent accidental arming. For reconnaissance missions, the payload bay houses stabilized gimbals with higher resolution electro-optical and infrared optics, along with data buffers for storing footage in case of comms loss. Payload management is not merely physical. The software stack includes arming logic, fuse timing, and target selection or discrimination algorithms that aim to maximize effect on intended military targets while reducing unintended damage. This interior orchestration of hardware and software is what allows relatively small airframes to have disproportionately large operational impacts. Let's move from hardware to performance. In a coordinated mission involving dozens of drones, performance is measured across several axes: range, endurance, speed, stealth, accuracy, and coordination. Range and endurance are driven by propulsion efficiency and energy density of onboard power sources. Many long range tactical drones are designed for multi-hundred-kilometer standoffs. They cruise efficiently at altitudes or low-altitude profiles optimized for fuel economy and low detectability. Endurance is also a function of payload. A heavy warhead reduces range, while a light reconnaissance package increases it. Speed matters in two phases, transit and terminal. For much of the flight, drones may travel at efficient subsonic speeds to preserve energy and remain less conspicuous. In the terminal phase, they can perform higher speed dives or terminal maneuvers to complicate interception and improve strike effectiveness. Accuracy is a crucial performance metric. Modern strike drones combine GPS guidance with visual or infrared terminal homing to deliver munitions within meters of designated targets. This precision reduces the need for high explosive yields and enables selective targeting of military infrastructure. In the Moscow strike scenario, the effectiveness of each drone's terminal guidance would determine whether critical infrastructure, command nodes, or symbolic targets were hit. Coordination among 93 platforms amplifies the effect. Swarms can perform saturation attacks to overwhelm detection and interception systems, staggered approaches to confuse deficit sensors, or distributed targeting to hit multiple assets simultaneously. Coordination algorithms may implement leader-follower behavior, decentralized consensus protocols, or pre-planned timing sequences that require precise clock synchronization across units. Survivability is also part of performance. Small signatures, electronic countermeasures, and agile flight envelopes make these drones difficult to intercept with conventional air defenses designed for larger aircraft or ballistic threats. However, defenders adapt. They deploy short-range air defenses, directed energy systems in some cases, and layered radar networks specifically tuned to detect low observable small UAS. The strike's success rate thus depends on the interplay between offensive capabilities and the defender's layered countermeasures. Safety features in these drones might sound paradoxical, but they are essential both from a military discipline perspective and to reduce unintended civilian harm. Built-in safeguards include arming interlocks that prevent payloads from being detonated at launch or in transit, geofencing that can prevent entry into sensitive airspace if desired, and self-destruct or disarm protocols if capture appears imminent. For example, a drone might be programmed to destroy its payload and scrub its memory if a tamper sensor detects a forced capture. There are also mission logic rules that attempt to identify and avoid densely populated civilian areas. Although in contested scenarios, these safeguards can be overridden by command authority depending on rules of engagement. Communications security is also a safety concern. Encrypted links and anti-hijack measures protect the drone from being turned against its originators, which would present both a tactical and propaganda disaster. Another safety angle is logistics and human handling. Many of these UAV are designed for ease of maintenance and safe handling by operators who may not be highly specialized. Quick change batteries, farming pins, and clear visual indicators reduce the chance of accidental detonation during preparation and transport. Finally, there is a psychological safety consideration. Operators can implement mission abort or stand down sequences to prevent escalation if political directives change mid-mission. What are the unique selling points, the tactical advantages that make a swarm of 93 drones a compelling weapon for a state like Ukraine in a conflict with a heavily militarized neighbor? First, the cost-to-effect ratio is enormous. Compared to aircraft or cruise missiles, Tactical strike drones are cheap to produce and can be fielded in large numbers. This asymmetry forces defenders to expend disproportionately expensive interceptors or to accept greater risk. Second, scalability and swarming. A single drone may be interceptable, but a large, coordinated group can saturate sensors and interceptors, increasing the fraction that reach targets. Third, modularity and adaptability. The same base platform can carry reconnaissance sensors one day and munitions the next, enabling rapid mission reconfiguration. Fourth, speed of innovation and manufacturing. Drones can be iterated on quickly with commercial off-the-shelf components and 3D printed parts, allowing field-driven improvements faster than traditional military procurement cycles. Fifth, strategic messaging. Striking a capital city's airspace is as much a psychological operation as a tactical strike. It demonstrates reach and disrupts perceived safe zones, both of which have significant geopolitical ramifications. The economics of drone warfare are a critical part of the story. Producing and deploying dozens or hundreds of tactical drones is comparatively inexpensive, especially when designs leverage civilian manufacturing techniques and components. This affordability allows smaller nations or non-state actors to purchase access to lethal aerial capability without needing the resources of a superpower. On the other hand, defending against swarms forces the defender to invest in layered and redundant systems, short-range air defenses, counter-UAS guns, electronic warfare specialists, and sensor networks, many of which are expensive to acquire and to operate continuously. That cost asymmetry changes battlefield calculus. An attacker can probe and exhaust defensive resources through repeated small-scale strikes rather than single massive, costly strikes. There is also an industrial economic angle. Drones drive demand for key components, sensors, avionics, batteries, microengines, which creates supply chains that can be resilient or fragile depending on geopolitics. Fielded success in a high-profile attack like the Moscow strike can catalyze further investment, foreign support, and domestic manufacturing POPs, while defenders might accelerate procurement of counter-UAS technologies, which in turn stimulates another industrial sector. The economic feedback loop is therefore rapid and impactful. Beyond hardware and economics, tactics and doctrine play a role. Coordinating 93 drones requires detailed mission planning, launch platforms and vectors, timing windows to exploit specific weather or radar conditions, jamming and deception plans to degrade air defenses, and redundancy for units that fail. The planners must consider the most probable defensive posture, identify soft spots or predictable behaviors in the air defense network, and synchronize drone behavior to exploit those windows. Swarm tactics can be kinetic, physically overwhelming interceptors, or cognitive, creating so many contacts that human operators and automated systems must split their attention, increasing the chance of misclassification or delayed response. Additionally, the attackers may use sacrificial units to trigger defenses, drawing interceptors away from higher-value drones that then reach their targets. Mission planners also need to anticipate legal and political ramifications, designing operations to minimize civilian casualties while maximizing military effect and psychological impact. What does the international and strategic reaction look like? A strike of this magnitude targeting a capital will prompt diplomatic fallout, statements, and potentially escalatory rhetoric. Analysts and militaries worldwide will study the tactics and the technical details, looking for lessons to apply in their own planning. Nations that had previously invested little in counter-UAS capabilities may find themselves rapidly reallocating budgets. Meanwhile, non-state actors will notice the effectiveness of relatively inexpensive drones and may attempt to replicate aspects of the tactic, raising concerns about proliferation and stability. The strike is both a demonstration of capability and a catalyst for global rethinking about urban and national airspace defense. Technological evolution will follow. Defenders will accelerate deployment of sensors tuned to small, low-signature airframes, expand counter-UAS patrols, and invest in scalable electronic warfare and directed energy solutions. Attackers, in turn, will seek to reduce detectability further, improve autonomous decision-making, and design more sophisticated swarm coordination protocols that are resilient to jamming and deception. The tug-of-war between detection and deception will intensify and will likely lead to hybrid solutions, combinations of kinetic interceptors, cyber/electronic countermeasures, physical barriers, and legal frameworks aimed at reducing proliferation. Lastly, the human dimension should not be overlooked. The psychological effect of drones over a city cannot be quantified solely by damage reports. The sight and sound of drones, the sirens, uncertainty about future strikes, and the symbolic intrusion into a capital all have civic and political consequences. Morale, public perception of security, and political will are affected in ways that translate into policy and resource shifts. In modern conflicts, the psychological front is as important as the kinetic one. To conclude, the 93 drone strike on a major capital is emblematic of a broader shift in warfare. It combines low-cost hardware, sophisticated interior systems, smart mission design, and strategic communication to achieve effects that punch far above the individual value of each platform. The exterior of these drones emphasizes stealth and modularity. The interior orchestrates resilient navigation, power management, payload control, and communications security. Performance manifests in range, precision, and swarm coordination. Safety features mitigate accidental harm and safeguard operators. Unique selling points highlight cost-effectiveness, adaptability, and psychological impact, and the economics tilt favor attackers who can mass produce inexpensive but capable systems. For military planners, policymakers, and technologists, the lesson is clear. The age of symmetric dominance by large, expensive platforms is challenged by low-cost, networked, and agile systems. The practical consequence is a global acceleration of both offensive drone capabilities and defensive countermeasures, producing a fast-moving technological and doctrinal evolution with profound implications for national security and civilian safety alike. If you found this analysis useful, detailed, and thought-provoking, please make sure to hit that like button, subscribe to Future Force, and share this video with others who want to understand the future of warfare. Thank you for watching, and I'll see you in the next deep dive.